This is a presentation on evolving Lindenmayer systems in a competitive environment. My name is Talle. This paper was based on my bachelor's project at the University of Groningen. Lindenmayer systems have been developed as a method of modeling plant growth. Originally designed by the Hungarian biologist Aristide Lindenmayer in 1968 to model algae growth, Lindenmayer systems have been expanded upon to model more complex species of plants. L systems are very suitable for modeling the repetitive structures found in plants. The example here shows the structure of a flower modeled using a Lindenmayer system. But these impressive applications are modeled by hand, so to speak. The systems are designed by humans. Our contribution proposes a method to evolve complex Lindenmayer systems that exhibit the same growth patterns that can be found in nature without the aid of human input. So the evolutionary process aims to simulate natural competition instead of aiming for a predefined output. The complexity that arises must be a result of natural efficiency and not the result of the author's desired output. Lindenmayer systems may have very complex syntax rules, but the basic mechanism is very simple. A system consists of an initial string of symbols called the axiom and a number of production rules. Repeated application of the production rules on the axiom changes the string of symbols that was originally the axiom. In the context of simulating plant growth, the string of symbols represents the phenotype or the structure of the plant. Every time the production rules are applied to the axiom, the plant grows. The example system consists of one rule, a single symbol axiom, and 2 rounds of application of these rules. So the axiom in this case is A, just the symbol A, and the one rule is A becomes ABA. So applying this rule once gives ABA, and applying the rule twice gives the string of symbols ABABABA. And that's how a system grows. Translating the string of symbols to 3-dimensional structures representing plants works by assigning meaning to the symbols. So we use so-called turtle graphics to model branches. A string of symbols obtained by applying production rules to an axiom is parsed from start to finish, and the head of the branch moves or rotates according to the symbols that are encountered. So the symbols serve as a blueprint for a 3-dimensional model. In this example, the plus and minus symbols signal the branch head to turn left or right, while the symbol M moves the branch head forward. This creates the shape seen on the left, so it moves forward once, turns left, goes forward, double turn to the right, forward again, one turn to the left, and one last step forward. And that gives this line. So we also use symbols that allow recursive branches to be encoded in strings of symbols. So a certain symbol starts a branch and another symbol closes a branch. And when a branch closes, the turtle moves back to the place it last branched from. So the 3-dimensional branches on the right were modeled using turtle graphics with branching. And this is the basis for our entire modeling system. There is not much more complexity in our system. Evolved Lindenmayer systems represent genotypes, or the DNA of plants, and applied modeled Lindenmayer systems represent the phenotypes, or the plant structures themselves. The string of symbols on the slide represents the aforementioned branching syntax. Because plants need to be able to form leaves as well, to be able to photosynthesize, 2 types of branches are created. Branches opening with square brackets are normal branches, while branches opening with a less than sign indicate that leaf material must be formed between this branch and all branches connected to this branch. The agent modeled by this string of symbols is shown here. Because the root branch opens with a leaf bracket, leaf material is formed between all branches splitting off from the root branch, and that can be seen in this image. There are 2 splitting branches and leaf material is created in between those branches. All plants in our simulation will be rendered using this syntax. The example here is 2-dimensional, but all plants in our simulations are 3-dimensional. Our evolutionary algorithm uses an environment to place agents in. Agents grow, compete, and reproduce in this environment. A typical simulation environment is shown. Soil fertility varies. The dark low spots are fertile valleys in which plants can grow bigger, and the lighter and higher regions are less fertile and will only support smaller plants. Fertile valleys are separated to simulate realism and encourage divergent evolution, which will be discussed later. When agents have been planted in an environment, they grow their three-dimensional representations. Examples of plants can be seen in these images. So the image on top shows a more densely populated area with competing plants, and the image below shows some smaller plants that are less developed. Every plant gets a score assigned. Score is influenced by leaf exposure to sunlight. So the sun moves in an arc-shaped path over the environment, and the strongest light is emitted at the highest point. Additionally, the angle of inclination matters. Leaves that orient themselves towards sunlight catch more of it. The efficiency of a plant influences score as well. The more sunlight per amount of plant matter, the more efficient a plant is. So plants are encouraged to catch as much sunlight as they can. Structural stability influences score by penalizing unstable structures, like top-heavy structures or plants whose center of mass is far away from their roots, or not above their roots. Finally, reproductive strength plays an important role. Reproductive strength is, however, not taken into account when scoring a plant. It's a different system. Instead, the next generation grows from physical seeds produced by plants. The seeds are rendered as brown spheres in these images. At the end of a generation, the seeds drop down onto the ground. Seeds contain their parents' Lindenmayer systems, so the DNA, so to speak, plus some random mutation on those systems. When all seeds are dropped, they are ordered by the score value of their parents. Seeds with the biggest score sprout first. Because seeds can only sprout when the area around them is empty enough, the best plants will always sprout first and leave no space for the worst seeds to grow. The interplay between score and seed sprouting selects the next generation. To quickly summarize the method, an environment is initialized where the environment varies in fertility, and seeds are planted in that environment. This is the first step of the simulation. Then seeds grow into their plants, and they are scored according to the criteria I discussed previously. The plants then drop their seeds. The seeds are ordered according to their parent score and produce the next generation of plants. The cycle then repeats. To illustrate our method, a typical simulation is shown. The image shows the very first iteration of a simulation. A simple terrain with one fertile valley is created, and seeds are dispersed along a certain interval. Seeds don't grow plants yet, they merely grow one seed. At the next generation, every seed will have produced one other seed until mutation creates advantages for them. After 20 iterations, the simulation looks roughly similar to the initial state, but some clusters of seeds have formed. This is caused by mutations in the Lindenmayer systems that produce these plants. Mutations have produced systems that produce more than one seed, causing clusters that quickly grow where the mutations occurred. At 80 iterations, a new strategy emerges. Most agents produce more than one seed. All single-seeded species are extinct at this point. A new way to compete arises. Tall plants can produce more seeds along their branch, and their seeds also disperse further away because they fall from a higher distance. The image shows that growing tall is clearly a winning strategy compared to growing close to the ground. After 130 iterations, mutations have caused the first leaves to occur. All leafless plants have zero efficiency, since efficiency is defined as the leaf-to-mass ratio. Even though the first leaves that evolve are inefficient, folded and crumpled up shapes, their non-zero efficiency will cause them to outcompete all leafless plants quickly. After 2084 generations, the leaf shapes have optimized themselves compared to their common ancestor. The image shows that they have specialized as well. Smaller leaves grow on simple plants at the infertile regions at the edges, while larger arc-shaped plants grow in the fertile valley. Additionally, the leaf shapes in the valley are starting to compete for sunlight by occluding other agents, so their neighbors. This dynamic will become more pronounced if the simulation runs longer. In fact, once leaves have evolved, all further specialization is driven by competition between agents. The first image shows a simulation in which plants are not allowed to grow dense, so they are not allowed to sprout close to one another. This means that competition for sunlight and space does not occur between neighbors. Therefore, plants stay very simple, regardless of the number of iterations the simulation runs for. The second image shows a simulation in which plants grow dense. Taller plants with bigger leaves develop here and constantly compete. The competitive cycle is endless. The simulation does not converge because there is always a strategy that beats the current population. Running several simulations with different parameters yields a large collection of strategies that have natural counterparts. Some of them are shown in the images. A lily of the valley on the left, palm leaves on the top right and nerved leaves on the bottom right. Rendered Lindenmayer systems are shown on the left here, while photos or illustrations of real plants are shown on the right. All successful strategies use the repetitive nature of Lindenmayer systems in one way or another, and at different scales as well. Divergent evolution occurs in the simulations. The difference in terrain facility is one of the most important causes of divergent evolution. When plants spread to different fertile valleys and develop more complex structures afterwards, they will not be able to spread through infertile terrain anymore, because they grow too large. The 4 plants shown here all have a common ancestor that existed about 1,000 generations ago. The strategies these plants use are very similar, but they have adapted to different circumstances. Some other interesting strategies can be seen here. The big leaves on the left are nerved, because leaf surfaces have a maximum efficient area. Subdividing the area with branches is essential for big leaves to be effective. Therefore, this strategy evolves whenever big leaves evolve. The plant in the center yields an almost perfect stability score because its center of mass is exactly above its root. In reality, of course, spring-shaped plants would not be stable at all, but that complexity was not taken into account in our simulation. Therefore, this individual has proven to be quite successful. The strange spikes on the right are not very efficient. These are leaves that have evolved very early on in the simulation, and they will develop into better leaves later. The first leaves that evolve do have some impact on the course of the simulation. The leaves shown here have a higher tendency to evolve into palm leaves, for example, that are more spiky, than into the broad leaves shown on the image on the left. Since one of our aims was to demonstrate that evolved strategies arise from efficiency instead of desired output, we have evaluated whether the leaves that evolve are not steered by the syntax we have chosen to use. The L-system syntax for modeling leaves is relatively complex. To ensure that the syntax does not influence the results, we have done simulations where the syntax was turned off. Instead, a single symbol encoded for a triangular leaf shape. Simulations showed that this change resulted in faster evolution of leafed plants, but the strategies did not change. The image on the left shows plants using the predefined leaf symbol. The image on the right shows plants using our normal leaf syntax. Evolving leaves using our syntax takes a bit longer, but it does not influence the strategies that evolve. Our model for DNA reproduction is very simple. It duplicates DNA and then mutates it. In genetic algorithms in general, sexual reproduction and crossover, for example, have proven to contribute to effective evolution. Our simulation does not model these interactions yet. There is no sexual reproduction at this point. The environment is currently static. The fertility and the shapes of the fertile valleys does not change over time. In reality, however, populations may be separated by rivers, changes in sea level, or climate change. Modeling these dynamics may yield more effective speciation. We have not observed the evolution of symmetry in our simulations. While Lindenmayer systems are very suitable for modeling recurring patterns, the simple syntax we have used has not proven to be able to model symmetry effectively, while symmetry is very common in nature, of course. Our model of natural competition between plants gives rise to strategies that can be found in nature as well, even though the Lindenmayer systems we are using are deliberately very simple. We have taken care not to steer plant development towards desired directions. Competition drives the evolutionary process. Complex strategies simply do not emerge at all when plants do not compete. A heterogeneous environment results in more diversity among species. Separating habitats allows for speciation and different applications of the same ancestral strategies. Thank you for listening. There will now be 10 minutes for questions.